For our summer project, inspired by our interest in music, sound, and improving everyday technology, we decided to look into active noise cancellation.
Although very difficult in practice, I thought of a Black Mirror style piece of technology where I could cancel out my friend's voice to the left of me and then maybe even enhance my friend's voice to the right of me.
So we wanted to see if there was any way to enhance the headphones by adding a directional component to the ANC. This means looking into the details of how ANC and sound localization or beamforming might work.
Over the next 10 minutes, we'll be exploring whether directional noise cancelling is physically possible and how close we can get using microphones, signal processing, and a Raspberry Pi.
First, we'll look at the theory we need to understand ANC and sound localization, so a good knowledge of wave physics. The key concept here is wave superposition. When two identical waves meet in phase, they constructively interfere, leading to an increased amplitude. And when two waves meet 180 degrees out of phase, they destructively interfere, leading to a decreased amplitude, so almost no sound. Destructive interference is the base of ANC. If we know how an incoming sound wave looks, we can generate the antiphase wave, which we can call antinoise. That would in theory cancel it out. Now, when the original sound wave and the antinoise wave meet at your ear, they destructively interfere, reducing the volume of sound you actually hear. The challenge is this must happen extremely quickly, so within fractions of a second. Otherwise, the waves won't line up and the cancellation will be ineffective.
Knowing exactly where sound comes from makes use of the fact that sound takes a finite amount of time to reach a certain place. For example, as humans, we're able to detect approximately where a certain sound is coming from, even with our eyes closed. Those particular sound waves will reach 1 year before the other. This order and time difference effectively allow our brain to calculate where the sound came from. Sound localization with microphones work in the exact same way.
In the first few weeks, we focused on research, what we would need and what our prototype would look like. Our initial idea was sort of like enlarged headphones with a clear cover to display the electronics for exhibition. Everything would be mounted on a cardboard cutout placed around a person's head with two identical environments, simulating the interior of an earphone. On either side, we would have a reference mic picking up the initial noise and an error mic picking up the slightly modified noise. These two mics work together, sending information back and forth through the Pi to work out what happens inside the environment, to decide on the anti-noise that the speaker will output.
Next, we started developing the code. The first test was to see how well our machine learning works. We started off with basic USB mics borrowed from the lab. However, we realized these were not sensitive enough. Instead, our phone mics worked well for test 1. Later, we would invest in MEMS mics which output digital audio directly. Using an adaptive filter, the algorithm predicted what the error mic would hear based on the reference mic signal. By comparing the two signals, the algorithm continuously updated itself and gradually reduced the prediction error. As the error approached 0, we knew that the system was successfully learning the acoustic transformation between the two mic positions.
After the upgraded equipment arrived, we began to solder and design the circuit. We now focus on the beamforming aspect. We placed two mics 22.5 cm apart and placed sound pulse of pink noise at known true angles, 1.5 meter away from the mic axis, and compare this with the angle detected. After adding an error approximator, we could see which determined angle have physically greater reliability. We use an algorithm called GCC-FAT to calculate the time delay and convert it into an angle by using known parameters like speed of sound, sample rate, etc. We conducted formal tests as described and some other informal tests.
It's pretty good. After many trials of rewiring the circuit, debugging, and even switching from Python to C++ last minute to reduce latency, we realized that performing beamforming and ANC simultaneously was extremely difficult at our scale. The two systems favored almost opposite operating conditions. For ANC, the ideal noise is low frequency, predictable, and repetitive, so that the algorithm has time to learn their behavior and generate an effective anti-noise signal before the sound reaches the listener. However, the beamforming process is easiest when there is a clear feature in a mid to high frequency audio signal, like a sharp spike, which can be identified in both mic channels. As a result, the types of sound that were easiest to cancel were often the most difficult to localize and vice versa, creating a significant challenge when attempting to combine both systems into a single demonstration.
For ANC, we noticed that results will be more significant if we can physically measure and visually represent sound amplitude decreasing, rather than us ourselves attempting to hear a decrease in sound. So, our final prototype simulated the ear canal and an AirPod-like environment with cardboard. Additionally, due to equipment limitations, we can only simulate one ear, since we're limited to 2 synchronized mics in one Raspberry Pi.
We split our concept into 2 demos with 2 sets of results. First, we'll look at ANC. This was the live demo we used at the exhibition.
And then I'll turn the ANC and see if it works.
We found that we achieved maximum cancellation, approximately 90%, at a mid-frequency of 440 Hz. Here we can see the learning curve when playing the signal for the first time and the instant cancellation when playing it for the second time. Unlike theory suggests, with low-frequency signals, we achieved a lower cancellation level, 60 to 70% on average. We also tested 2 and 3 frequencies simultaneously, noticing that the greater the number of simultaneous frequencies, the lower the cancellation level.
To evaluate the beamforming system, we analysed many different performance metrics. The first graph compares the true speaker angle with the estimated angle to see if the beamformer points in the right direction. We can see a strong linear relationship between the true and estimated angle. However, at larger angles, the estimated angle begins to deviate from the line and the size of the error bar increases, which does not occur at the negative end. The second graph shows the absolute error as a function of angle. This is our main measure of accuracy. Across the central region, the error remained below 3 degrees. Again, the larger errors occurred at the extreme positive values where the asymmetry in error can be seen. The third graph measures if the beamformer gives repeatable results. Here, we can investigate accuracy versus precision and can see a larger standard deviation at negative 75 degrees, despite its absolute error remaining below 3 degrees as seen before.
For both sets of results, we saw a few things that are different than what theory would suggest. Theory would suggest that lower frequencies would show maximum cancellation, as they would give the system more time to generate the anti-noise signal. We believe this is due to our hardware. The initial signal came from an iPhone speaker, which is small, so it's unable to produce low frequencies well. Other harmonics tend to become more significant. We actually saw this at the start of the project, when our frequency detector displayed 300 Hz instead of 100 Hz, 303 instead of 101, and so on. If our anti-noise speaker had the same issue, the anti-noise generated also may not have been that accurate. And here are some of the improvements we could have made, including changing the speakers and improving the code. For sound localization, in the graphs earlier we saw bias on one side of the system with higher uncertainty on one of the sides. We believe this is due to reasons such as the wave getting distorted by objects and walls, and even maybe uncertainty in the initial measurements of the true angles. With more time, we would actually rotate the setup and take more readings. Also, we would use more than 2 mics, which is actually key to improving the whole project.
This is the main improvement that we'd make to begin an integrated directional ANC system. Our system was limited because the mics only gave us 2 usable audio channels left and right. This was enough for a reference microphone and an error microphone, but it was not enough to run beamforming and ANC at the same time. To fix this, we could use hardware designed for more than 2 synchronized mic channels. For example, we could use a 4-microphone array board or a multi-channel audio interface. This would allow the Raspberry Pi to receive 4 separate microphone signals at the same time, all sharing the same clock, meaning they capture audio samples at the exact same rate and moment. With 4 channels, we could dedicate 2 or more microphones to beamforming and direction estimation, while still keeping a separate error microphone for ANC feedback. With just 2 reference microphones, directional estimation is only valid in a 2D plane, and full 3D localization required a minimum of 4 reference mics. So the main improvement would be to design it around the required minimum amount of audio channels from the very start.
So in conclusion, we've simulated ANC ourselves and we've analysed sound localization. So to answer the question, yeah, we believe that in theory we could cancel all sound and amplify just the direction we'd want to keep using real beamforming. In reality, we would need ways to reduce wobble and ensure it's a pleasant listening experience, which we would be able to do if we had a fully integrated system. This sort of directional component would be more achievable than cancelling solely from one direction due to the directional differences in phase that would need to be accounted for.